Hello everyone, my name is Dimitri and today I'm explaining thermal stress in a system with an iron bar and an aluminum bar. So each of these bars is 1 meter long and they are placed in a series between two rigid walls. The temperature increases by 100 degrees Celsius, but the walls do not move, so the total length must stay at exactly 2 meters. The iron bar has a thermal expansion coefficient of 12 times 10 to the minus 6 per degree Celsius and a Young's modulus of 210 gigapascals. The aluminum bar has a coefficient of 24 times 10 to the minus 6 and a modulus of 70 gigapascals. If the bars were free to expand, we would use the formula delta L is equal to alpha times L times delta T. So for this iron bar, it gives about 1.2 millimeters of free expansion, and for the aluminum bar, it gives 2.4 millimeters. So together, that would freely expand 3.6 millimeters. But because the walls are rigid, the bars are not able to expand at all. So instead, the walls just push back on the bars, and then in reaction, both bars develop internal compressive stress. So strain and equilibrium equations. So the total strain in each bar is made up of two parts: thermal strain, which is alpha times delta T, and mechanical strain, which is sigma over E. So the strain equation is epsilon equals alpha delta T plus sigma over E. Because the bars are in series and the total length cannot change, the strain in the iron bar plus the strain in the aluminum bar must equal 0. And because the bars carry the same internal force, the stress in each bar is the same. So using these ideas together gives the stress formula which will be used for the calculation. When we plug in the numbers, the sum of the thermal expansions is 0.0036. The sum of the reciprocals of the moduli is 1.90 times 10 to the minus 11. And dividing these gives a stress of negative 189 megapascals. The negative sign just simply means that the stress is compressive. And both of these bars are experiencing the same compressive stress. So for the final length and conclusion, we now calculate the final length using the total strains. So for the iron, the final strain is positive 0.0003. So the final length becomes 1.0003 meters. For the aluminum, the final strain is negative 0.0003. So the final length becomes 0.9997 meters. And adding both of these bars together gives us exactly 2 meters, which matches the fixed wall spacing. So in summary, both bars develop 189 megapascals of compressive stress, and the iron bar becomes slightly longer, and the aluminum bar becomes slightly shorter, and the total length remains exactly 2 meters. And this concludes my presentation.
All right. Hello, everyone. My name is Jack, and for my part of the project, I focused on the diffusion data that we collected from the diffusion simulation and how it supports the diffusion equations that we were given. And I recorded how many blue atoms crossed the midpoint for every 5.5 picoseconds for 30 picoseconds under the three different conditions. The first run was 200 atoms at 300 Kelvin, then 100 atoms at 300 Kelvin, and finally 200 atoms at 50 Kelvin. So let's start with the first data set, which was the um, 200 atoms, 300 Kelvin run. So in this Excel sheet that I made, here's the time and the number of atoms to the right, and then the average temperature as well. We also recorded the flux in here, which I will get to in a second. So for this simulation, there's 200 blue atoms on the left side with a temperature of 300 Kelvin. And to find the diffusion flux, basically, which is J, which is given by this equation right here, which we'll talk about later, which is also equal to just the change in the number of atoms over the temperature. So given this, I used it's basically like y2 minus y1 over, or other way around. It's just the change in the number of atoms, which is given right here. So we take the most recent one, subtract it from the previous one, and then same thing for the time, most previous subtracted from the recent one, and that should give you the flux. So yeah, basically this formula helps us calculate the change in atom number between the two time steps divided by the time interval in this case, which is the 0.5 picoseconds. And it tells us how quickly the atoms are crossing the midpoint, which is essentially the diffusion flux. For this run, we see that the number of atoms on the right side increases steadily from about 0 all the way down to around 115 over the 30 picoseconds. And the flux starts high at the beginning, and I'll show a graph later where we could see that it gradually decreases, which makes sense because the concentration difference between the two sides becomes smaller as diffusion progresses. Now, if we go to the second run here, which is the 100 atoms at 300 Kelvin run, I reduced the number of atoms to 100 but kept the same temperature. And there were fewer atoms to begin with, which means the initial concentration gradient was smaller. And if we use the same formula for the flux, which we have, you can tell and notice that the flux values were overall lower than the 200 atom case. So here, if you see that we have 0, 2, 2, 2, a lot of 2s, 4s. If we go over to this one right here where we had 200 atoms at the same temperature, we can see some 10s, 6s, and some 8s. The total number of atoms on the right side reached one ended at around 54 for the 30 picoseconds compared to 115. This clearly shows that there was fewer atoms, meaning a smaller gradient, which means the diffusion happened more slowly, which this matches our expectations from the diffusion of the flux equation. Now, if we go to 200 atoms at 50 Kelvin, we can see that at this lower temperature, we should assume that the atomic motion should slow down because the particles have less thermal energy due to the lower temperature. So through the 30 picoseconds, we can see that the number of atoms on the right side only goes to 47, which is less than what happened at 300K Kelvin. Sorry. So yeah, even though the concentration gradient was the same in the first run, the diffusion rate was drastically reduced, and this is because the temperature was reduced by 250 Kelvin, and this clearly shows the effect of the temperature on diffusion behavior. So now if we go over here and we look at the graphs, this is the diffusion of the atoms versus time. Here are the 3 different runs, and this is the diffusion flux on the first run that we had, which is the 200 atoms at 300 Kelvin temperature. So if we look at the graphs, I plotted the number of atoms on the right side here versus the time, and we can see that the 200 atoms at 300 Kelvin drastically increased the diffusion, and then we can see the other ones that were either had lower atoms or lower temperature were more steadily and increased slower. So yeah, the steepest slope is going to be the 200 atom at 300 Kelvin temperature. So yeah, basically this graph can help us discuss on how 2 equations that we were given can relate to the diffusion versus time. This is going to show how the number of blue atoms moving to the right increases for 200 at 300 Kelvin, how they run. Slower for this run, and then it was very slow for the 200 atom at 50 Kelvin run. And for the estimated flux versus time, we know that the flux starts higher and then it gradually decreases as the system approaches equilibrium as more atoms get to the right side. So basically, these plots confirm that J is equal to negative D, which is given by dC over dx. This just means that the greater concentration gradients leads to a higher flux, and D equals D naught E to the negative ED over KBT. This just means that the diffusion is exponentially faster at higher temperatures. So if we were to explain the 2 flux equations, this first equation here that's given right here, this equation says that the diffusion flux is proportional to the concentration gradient, And our data clearly supports this relationship because when the gradient was higher, like in the 200 atom run, the flux was also higher than the other two runs, which is clearly shown in these two graphs. And also in the data points here, we can see that the flux was generally higher than these two. So this makes sense. And the negative sign for the D in here, that just means the diffusion goes from a high concentration to a low, which matches what we observed. And for the temperature dependence of D, given by this equation right here, this equation means that temperature increases as the diffusion coefficient increases exponentially. And if we compare the 200 atom runs at 300 Kelvin and 500 Kelvin, we know that the flux was much higher during the 300 Kelvin. So we have 2, 4, and then over here, no 4s available at all. So we know that the flux was higher during the higher Kelvin temperature ones. And that's because at higher temperatures, atoms have more energy to overcome activation barriers. So this means the diffusion speeds up. And this matches perfectly with our theoretical data that we got. So overall, the 3 data sets that we concluded from the 3 runs given here, as well as the graphs that we had, this shows that the diffusion flux is directly related to the concentration gradient, which supports J is equal to negative D, dC over dx, as well as the diffusion rate increased strongly with temperature, which supports the second equation here, which is D is equal to D naught E to the negative ED over KBT.